Welcome to the Conservation of Energy video. In exercise 1, we'll be using different masses to compress a spring and calculate its spring constant. This is the motion sensor. It emits an ultrasonic pulse which reflects off of a target and returns to the sensor. Using the time it takes to return, the sensor is capable of establishing the position of the nearest object.
First, we'll set up the apparatus. Mount the track on the base as shown. For this exercise, the track will need to be approximately level. To achieve this, measure the heights at each end and adjust as needed.
Tie a string to the end of the spring launcher. Thread the string through the hole in the end stop and over the pulley.
Place the cart such that the spring is uncompressed and touching the end stop. Measure the initial position of any part of the cart. Hang a particular mass from the string and measure that part's new position. Record the mass and displacement and repeat enough times to make a decent graph. Note that you should disregard any data obtained with the spring fully compressed.
In exercise 2, we'll be measuring the effect of friction on the motion of the cart.
Attach your motion sensor to the end of the track and plug it into the data acquisition interface.
Turn the motion sensor so that it points at the cart.
Press record in Capstone and give the cart a gentle push.
Allow the cart to come to a complete stop on its own and press stop.
You will need to use the slope of the linear portion of this graph to determine mu. If you would like to see a preview in Capstone, you can select the linear portion and add a linear fit as shown.
Repeat this process 5 times, always pushing the cart in the same direction. You can use this data to find the uncertainty on your slope. Next, reverse the direction. If the slope magnitudes in each direction are within uncertainty, your track is level and you can proceed to collect data. If the two slope magnitudes are outside uncertainty, adjust the height of the feet until they are within uncertainty.
Now press record again and give the cart a push. You can collect slopes in both directions in a single run by letting the cart bounce off the end stop. Take 5 trials for a total of 10 slope values. Use these to find mu.
In exercise 3, we'll be launching a cart up an incline and plotting the maximum gravitational potential energy plus the work done by friction against the initial potential energy stored in the spring.
Raise the end of the track. It should be high enough that the cart doesn't hit the sensor when fully plunged. Aim for a minimum of about 25 centimeters from the table. You will also need to measure the angle the track makes with the horizontal. Probably the easiest way to do this is to measure the heights of 2 different points on the track and use the scale on the track to find the distance between them. Using this method, the difference in heights will be the opposite side of a right triangle, and the distance along the track will be the hypotenuse.
Remove the string from the launcher to help minimize friction.
In Blackboard, download the experiment file called Conservation of Energy and open it in Capstone.
Press record, pull back the launcher, and release the cart. The horizontal line at the beginning represents the initial distance from the cart to the sensor. As you pull back the cart, that distance increases and the second horizontal region occurs when the spring is compressed. As such, the difference between these is the compression of the spring. The parabola represents the path of the cart, so the maximum gravitational potential energy occurs at the minimum of the parabola.
Repeat this for many different plunge depths over as wide a range as possible.
Thanks for watching the Conservation of Energy video. Due to university courses being required to maintain a certain average, students' marks are also conserved. So if you can't make your lab better, just make everyone else's worse and you'll do just fine.